this is ELEC120 problem sheet 1, solution to question 1c. So this question is a calculation question. Here we're going to calculate the values using the important equations that we've learnt so far about electrostatics. So this will use a lot of the important equations which you've got on this part of your handout. So we've defined Coulomb's law, the electric field strength, the work done, which is potential energy, and then potential. It's important not to get these two things confused. So potential is different from potential energy, and work done is equal to potential energy, and that will help you understand if you can just get your head around that those are the same thing. So work done is basically you put work into the system, and that's the same as the potential energy, because we can potentially release that from the system and get it back. And we'll talk more about this when we look at capacitors in a little while in the lectures. So here we've got, calculate first up the electrostatic potential, 5 millimeters from a negative charge of 5.561 times 10 to the minus 10 coulombs. So important things, we're looking for the potential, and it's 5 millimeters from a negative charge of this magnitude. So those are our important values. So how do we go about solving this? Well, what I've done is, first up, I've said we want the electrostatic potential. So we want to find the potential, and we know that's in volts because this is the potential here. We're using this equation. And then I've just written down my important terms that I'm going to put in the equation. So R is 5 millimeters, and Q is minus 5.561 times 10 to the minus 10 coulombs. We just put that negative sign because it's a negative charge, but if we're interested in the potential, it doesn't really matter because it's just giving us a direction. So you've got a magnitude and you've got a direction, but that's kind of complicated, but you'll get used to it as we go through and continue our lectures. So all I've done here is I've written the equation that I need to use. Good exam tip is to always write the equation that you're attempting to use. So if you do use the wrong equation, then you can get follow-on marks. So you only lose the original marks and not all of the ones that follow. If I can understand what you've done, I want to try and give you marks. So please try and make your work easy to follow. So all you need to do is put the values into the equation. So here's Q. 4 pi epsilon naught, so there's epsilon naught there, which again you'll be given in an exam as a constant, but you'll probably know it anyway. And then that's R that I've put in. Note this one isn't R squared. I made a mistake when I started to work this out. Don't worry if in your exam you have crossings out and stuff. So the main point of these problem sheets is they're not beautiful solutions, but you can see what sort of working level you need to do. So just work this out and you get a voltage of minus 1000 volts. So it's a potential of 1000 volts, it's just in the negative direction, because we always refer things to ground, which is how it works. Okay, so that's solved. Next up we're going to do part 2, which is to find the electrostatic field strength E at this position. So the position is 5 millimeters. We still have Q, that's the same. And we're going to find field strength E. So which equation are we going to use? We're going to use the equation for electric field strength, which is this one up here, and we're just going to substitute our values in again. So here we go. We want to find E. I know it's in volts per meter. Please remember your units when you're giving an answer. It's really important. If you don't give the units, your answer is essentially meaningless, and please don't do that. So here's my equation. This time I've got R squared. Put your values in. I haven't put the direction in this time, I've only calculated the magnitude. Remember, the negative symbol is just telling us which direction the field is in. So put your numbers in, and make sure you square R this time, and then you get out a value of around, I've rounded this so it looks neat, of 2 times 10 to the 5 volts per meter. And if you can imagine, this would be going in towards that charge because the charge is negative. Remember, the negative symbol is just giving us the direction. Right, so that's done. That's 3 marks. See, these are past exam questions and we are racking up the marks. This is good. Part 3, we're going to calculate the force exerted on a charge of plus 10 to the minus 9 coulombs placed at that position. So again, the same position as 5 millimeters. Okay, so here we go, let's scroll down. There are two ways you can calculate this. Both give you the same answer, which is fine. There's a quick way. So we're looking at the force exerted on a charge Q2, which is a value of 1 times 10 to the minus 9, and it's positive at a distance r of 5 millimeters. There's a quick way where you can say force is equal to the electric field times the charge. We've already calculated the electric field, remember. This is shown on page 63 of your lecture notes if you want to go and have a look. And if you put the values in, you find you get a force of 2 times 10 to the minus 4 newtons. Or you can do it another way around, and you can use the important equations. So here, this is the equation for force. This is the other way we can calculate it. So we've got our two charges. Q1 was the original charge. Q2 is the new charge that we're looking into. These are constants, and we know that R is 5 millimeters as before. So this is using this equation. Put your values in. Remember to square R here, and you will get a force of 2 times 10 to the minus 4 newtons, which is the same as this one, which is good. So it doesn't matter which way you do it, you get the same answer. And finally, part 4, we're going to find the potential energy of the final system. So this is using this equation here. So the potential energy is equal to the work done. This is when I said, remember that potential energy is the same as work, so you need to use this equation. So we're just going to put our values in and see what we get out. So we're looking for the potential energy of the system, i.e. work in joules. So we can use our equation. Work is equal to Q1 Q2 over 4 pi epsilon naught R squared. Put your numbers in, and you get work is 1 times 10 to the minus 6 joules. Or you can use the alternative version. Remember that work is equal to the change in voltage times the charge. This is in your notes as well, and you can put this in. So the voltage is minus 1000, which we had before, times minus Q2. This is in your lecture notes in, where is it? Let's find it. It was in the equipotential bits. Yeah, so work is equal to Q times delta V, which is the alternative way we're doing it here. And that's the equation we used. So if you put it in, you should get the same answer out. So work is equal to 1 times 10 to the minus 6 joules as before. And that's the end of question 1. So that was from a past exam question, and if you've got all of those right, you're doing very well.